In this special episode of the SkatterBencher guides, we're overclocking the Ryzen 7 9700X up to 6325 MHz using the ultimate form of CPU cooling, liquid nitrogen. In this video, I share two distinct overclocking strategies. First, we rely on the OC strategy number 5 from SkatterBencher 78 and simply improve the cooling. Second, we maximize the precision boost performance by leveraging the extra thermal headroom to increase the frequency with asynchronous eCLK. However, before we jump into the overclocking, let's first have a look at the hardware, the benchmarks, and let's get back up to speed on what we did in SkatterBencher number 78. The AMD Ryzen 7 9700X is part of AMD's Zen 5 based Ryzen 9000 desktop processor product line, codenamed Granite Ridge. The Ryzen 7 9700X has a base clock of 3.8 GHz and a listed boost frequency of up to 5.5 GHz. In SkatterBencher number 78, I demonstrate the performance tuning options of the Ryzen 7 9700X in 5 unique overclocking strategies. In the final, most advanced strategy, we push the processor up to 5860 MHz with AIO cooling. The system we're overclocking today consists of the following hardware. For this guide, I traveled to the Elmo Labs office in downtown Taipei and was able to use the platform he used to break the 3D Mark CPU profile 16-thread record a couple of weeks ago. The CPU, memory, storage, and graphics card are the same as in the original SkatterBencher guide. The key to success for this overclocking guide is the Elmo Labs Extreme Overclocking products, including the Volcano CPU container and the Hot 300 heater components. We use the same Windows 11 and benchmark applications to measure performance and ensure system stability. Before we head down to the negative temperatures, let's first have a look at the performance improvements that we achieved in SkatterBencher number 78 with plain AIO cooling. Here are the precision boost 2 parameters we used in OC strategy number 5. Here's the benchmark performance improvement over stock. Here's the 3D Mark CPU profile performance improvement over stock. And here are the AIDA64 memory benchmark performance improvements over stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 5391 MHz with 1.15 volts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5494 MHz with 1.222 volts. The boost frequency at one active thread is about 5758 MHz, and the average boost frequency gradually trails off to 5454 MHz when all cores are active. All 8 cores can boost to well beyond 5.8 GHz in single-threaded workloads. Of course, with our ultimate CPU cooler, we can reduce the operating temperatures significantly. And that's exactly what we'll do in our first overclocking strategy. In our first overclocking strategy, we simply take advantage of the cooling benefits of liquid nitrogen. An effective setup for liquid nitrogen cooling consists of 2 key elements: the LN2 container in which we pour the nitrogen and a backplate heater to help with the condensation. Experienced AMD Ryzen CPU overclockers are well aware there are 2 ways to overclock your Ryzen CPU: Precision Boost Overdrive and with OC mode. With Precision Boost Overdrive, we fine-tune the Precision Boost 2 boosting algorithm, which is active by default on all AMD Ryzen CPUs. The main advantage is that you maintain the maximum boost capabilities for both 1T and NT workloads. In OC mode, we disable all automatic boosting technologies and associated telemetry. It enables us to set a specific frequency and a specific voltage and allows us to run at higher temperatures, which helps maximize the performance in specific workloads. The upside is that sometimes you get better performance than with Precision Boost. However, you always sacrifice performance in 1T workloads due to the lack of automatic boost. Traditionally, extreme overclocking the AMD Ryzen CPUs is done with OC mode. But for this guide, I wanted to stick with Precision Boost and see how far I can push the algorithm. Now, that might sound very straightforward, but it's not really. And that's because the Precision Boost algorithm heavily relies on the CPU's VFT curve, not the VF curve, and that one little letter makes all the difference when we use extreme cooling. Let's start with the basics. What is a VFT curve? Well, simply put, a voltage frequency temperature curve describes the relationship between an operating frequency, the operating temperature, and the voltage required to operate at that frequency and temperature. While every modern SoC has a factory-fused voltage frequency curve to dynamically adjust the power consumption depending on the workload needs, not all SoCs have a temperature aspect. It's not easy to visualize a VFT curve because it has three dimensions: voltage, frequency, and temperature. So how about we first look at a VF curve at a fixed temperature and then change the temperature and see what it does to our VF curve. Here's the default voltage frequency curve of this Ryzen 7 9700X at an operating temperature of 50 degrees Celsius. Let's now add the VF curve of the same CPU but at an operating temperature of 0 degrees Celsius. We can immediately make a couple of important observations. First of all, clearly, this CPU has a different voltage frequency curve at different temperatures. This clearly outlines that we should always talk about a Ryzen's VFT curve rather than the VF curve. Furthermore, the VF curve deviates more at higher frequencies than at lower frequencies. For example, the difference at 4550 MHz between 0C and 50C is only 36 mV. However, at 5.5 GHz, the difference is 150 mV. Lastly, we can see that at a similar voltage, there's much more frequency headroom at lower temperatures. For example, 1.2 volt yields 5250 MHz at 50C, but 5550 MHz at 0C. The cool thing, literally, is that Precision Boost also scales with negative temperature. In this chart, we measure the operating voltage at different operating temperatures with the CPU at 5.3 GHz running a light all-core workload. We find that at high, near TJ max temperatures, almost 1.3 volt is required for 5.3 GHz. However, at 0 degrees Celsius, it only needs less than 1.15 volt. At minus 50 degrees Celsius, the operating voltage is below 1.1 volt. The general takeaway is that by reducing the operating temperature with better cooling, we essentially warp the Precision Boost VF curve. Now, warping the VF curve is something we can also do with another tool, asynchronous eCLK. In the final overclocking strategy of SkatterBencher number 78, I explain how you can use asynchronous eCLK to overclock the Ryzen 7 9700X. I won't cover it in great detail here, so suffice to know that what we do when we use asynchronous eCLK is that we stretch the VF curve along the frequency axis. In OC strategy number 5 of SkatterBencher 78, we use an eCLK of 104.3 MHz. This is what such a curve looks like. Using asynchronous eCLK for overclocking works in two ways. It undervolts and overclocks at the same time. You can see, for example, that our default curve demands 1.126 volt for 5 GHz, whereas our eCLK curve only demands 1.085 volt. Also, at 1.3 volt, with eCLK we get about 230 MHz more than with the default curve. The eCLK adjusted curve looks a lot like our temperature adjusted curve, but it's not exactly the same. We find that generally the 0 degree curve provides slightly more undervolting across the majority of the curve. However, at the very upper end of the curve, the impact of eCLK is more significant as we reach higher frequencies. But what if we get the best of both worlds? Asynchronous eCLK and lower temperatures. Now the curve is starting to look pretty impressive. Not only do we get the most undervolting at the lower end of the curve, 5 GHz at only 1.045 volt, we also get significantly higher frequencies at the upper end of the curve, up to 6 GHz at 1.387 volts. Now that we know that simply lowering the temperature will give us higher frequencies, let's have a look at the impact on the performance. The BIOS configuration that we use for this OC strategy is identical to the one of overclocking strategy number 5 in SkatterBencher number 78, except we don't use the curve shaper. We reran the benchmarks and checked the performance increase compared to the default operation. With the liquid nitrogen cooling, we essentially eliminate any thermal-related performance throttling. As the CPU is now running at 6 GHz across all cores in 1T and NT workloads, we see a significant performance improvement across the board. The geomean performance improvement is plus 13.77%, which is 2 percentage points better than with our AIO-cooled system. We see a maximum improvement of plus 43.44% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 5,939 MHz with 1.184 volts. The average CPU temperature is minus 48.2 degrees Celsius. The average CPU package power is 174.8 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5,993 MHz with 1.289 volts. The average CPU temperature is minus 24.7 degrees Celsius. The average CPU package power is 174.7 watts. The boost frequency at one active thread to all active threads is about 6 GHz, and each of the 8 cores can boost to nearly 6 GHz in single-threaded workloads. Before we move on to the next overclocking strategy, I want to share this chart with you because I think it beautifully illustrates the impact of lowering the operating temperature on the operating voltage and frequency. In this chart, we're cooling down the CPU from 85 to minus 40 degrees Celsius while running an all-core workload. We can distinguish 3 phases. In the first phase, from 85 to 40 degrees Celsius, the precision boost algorithm gradually allows higher voltages. At 85 degrees Celsius, the maximum allowed voltage is 1.3 volt, and at 40 degrees Celsius, it's 1.375 volt. During this phase, the frequency increases from 5,575 MHz at 1.3 volt to 5,825 MHz at 1.375 volt. In the second phase, from plus 40 to about 0 degrees Celsius, the operating frequency continues to increase while maintaining the maximum allowed voltage of 1.375 volt. This is the effect of the VFT algorithm. By decreasing the temperature, we undervolt the CPU. And as a result, gradually, higher and higher VF points on the VF curve drop below the voltage threshold. At 40 degrees Celsius, we get 5,825 MHz for 1.375 volt, and at 0 degrees Celsius, that's 6 GHz. In the third phase, from 0 to minus 40 degrees Celsius, the operating voltage continues to reduce as the temperature gets lower. This is the best visualization I could come up with to illustrate the precision boost VFT curve. At 0 degrees Celsius, we get 6 GHz at 1.375 volt, but by the time the temperature has dropped to minus 40 degrees Celsius, we only need 1.25 volt for the same 6 GHz. In our second and final overclocking strategy, we try to maximize the precision boost algorithm using asynchronous eCLK and curve shaper. Now, in the previous overclocking strategy, I already demonstrated that lowering the temperatures has a direct impact on the operating frequency and the performance. But using liquid nitrogen and much lower temperatures has a secondary advantage as well. It increases the overclocking headroom. And that's exactly what we'll explore right now. Observant viewers will have noticed something important about the VF curves shown in the previous overclocking strategy. They all end at approximately 1.4 volt. I've discussed this at length in the original SkatterBencher guide for the Ryzen 7 9700X. The long story short is that this CPU has a voltage limit for all core workloads of 1.35 volt. We can increase this slightly to 1.375 volt by adjusting the Precision Boost Overdrive scaler to 10x. But that's about it. Furthermore, the voltage limit for 1T workloads is 1.4 volt, though we sometimes see slight excursions up to 1.45 volt in idle scenarios. This voltage limit is a severe restriction on our overclocking capabilities because we cannot leverage higher voltage to achieve higher frequencies. However, we can use the Precision Boost Overdrive toolkit to push harder below the voltage threshold. Specifically, we can use a positive curve optimizer. Contrary to using negative curve optimizers, when we use positive values, we actually overvolt the VF curve. Here's what happens when we apply a plus 30 curve optimizer to our VF curve from OSI strategy number 1. We can see that the entire curve has shifted upwards along the voltage axis. We not only need a lot more voltage for a given frequency, but also our maximum frequency has decreased significantly. At first sight, this looks like a terrible idea. However, we can now utilize asynchronous eCLK to push up the frequency again. For example, this is what the curve would look like with a 110 MHz eCLK frequency. Compared to the previous overclocking strategy, at 110 MHz eCLK, we need more voltage for frequencies below 5.9 GHz. However, we get higher frequencies above that. With this starting point in mind, I set about my extreme overclocking journey. The manual tuning process for asynchronous eCLK can become quite convoluted because it spans a wide range of applications, going from light single-threaded workloads all the way up to heavy all-core workloads. When we're trying to tune our CPU, whether that's with curve optimizer or with asynchronous eCLK, essentially what we're looking for is the weakest link across our VF curve and across all the applications. Now, in preparation for the SkatterBencher guide with the Ryzen 5 9600X, I found that the Y-Cruncher BKT workload is usually the first one to show signs of instability. I load up the Y-Cruncher BKT and run it on all cores. Then I gradually decrease the temperature from plus 80 degrees to minus 50 degrees. Unfortunately, I quickly noticed that the system became unstable at around plus 48 degrees Celsius. To address this issue, I use Curve Shaper and set a positive magnitude for medium, high, and maximum frequency at high temperatures. That resulted in a slightly more stable system, as it only crashed around plus 37 degrees Celsius. Then I also set all medium temperature points to plus 15, which resulted in a stable system. Our final VF curve at minus 50 degrees Celsius now looks as follows. We can see that technically, our VF curve is not as good as the final strategy of SkatterBencher number 78 because we're not running that low of a voltage below 5.3 GHz. But that doesn't matter because due to the sub-zero temperature, our CPU always runs at 6.325 GHz. That's the highest available point on our VFT curve. We reran the benchmarks and checked the performance increase compared to the default operation. The additional thermal headroom provided us with another 500 MHz over our best overclocking strategy from SkatterBencher 78. That translates into another impressive jump in performance across the board, except for our gaming benchmarks, which barely improve even at the much higher frequencies. The GeoMe performance improvement is plus 16.24%, and we get a maximum improvement of plus 43.47% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 6115 MHz with 1.188 volts. The average CPU temperature is minus 47.8 degrees Celsius. The average CPU package power is 179.3 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 6321 MHz with 1.294 volts. The average CPU temperature is minus 48.1 degrees Celsius. The average CPU package power is 178.8 watts. The boost frequency at one active thread to all active threads is about 6325 MHz. And each of the 8 cores can also boost to 6325 MHz in single-threaded workloads. Alright, let's wrap this up. This was the very first time that I used Precision Boost in combination with extreme cooling. And it was kind of cool to see how the dynamic VFT curve behaves with negative temperatures. But it's also very cool to figure out what's the best combination of asynchronous eCLK, curve optimizer and curve shaper to maximize the frequency. And it must be said, if we didn't have the curve shaper temperature points, our overclock would be a lot worse because we needed the curve shaper temperature points to get our system stable at ambient temperatures. Also, the performance improvement is, of course, quite impressive. We're running at 6.3 gigahertz. However, the gaming performance is pretty weak. I didn't see any improvements going from our AIO cooled system to our liquid nitrogen cooling. I would have figured that at least there would be some kind of improvement in performance, but there really wasn't that much. So that's a bit odd. Anyway, that's it for this video. I want to thank you for watching and the patrons for the support. If you want to read through my BIOS settings or check out the results, I'll also have a written version of this video up on my blog. And if you have any questions or comments, drop them in the comment section below. See you next time.